Architectural Outcast.
Welcome to the Architectural Outcast. The channel helps y'all learn to think like an architect. I'm Randy. The collapse of the World Trade Towers really shook up the architectural world. You had some pretty serious discussions in some quarters about how maybe we shouldn't be building tall buildings anymore. They were just too dangerous, too easy a target. I was in architecture school when the attacks came. In fact, I was supposed to be in class that morning. I was sitting there like everybody else in shock when I got a phone call from my professor. She said, "I don't think we should be having class today." It's like, yeah, I agree with you. The architectural world is very small. Everybody knows everybody, or at least you know somebody who knows somebody. A number of my professors and colleagues, they knew the architects and architectural engineers down at ground zero responsible for figuring out what happened. Within hours after the dust settled, we had information coming back to us. Now, this was more than some morbid curiosity. Our professor was at stake. As I said, we had been really shook up, and there were serious voices saying we shouldn't even be building skyscrapers anymore. They were too dangerous. So we had to come to terms with what exactly happened and why. For several years, we had multiple classes and seminars dedicated to trying to understand exactly what happened, beginning with the attack in the early 90s and how that led to overconfidence, to analyzing every aspect of how the buildings reacted on that tragic day. Just because something was common knowledge then doesn't mean it's common knowledge today. And I've been reminded here recently, just because I know something doesn't mean everybody else knows it. Within a couple years after the attacks, we started to hear stories. Buildings don't act that way. There's no explanation as to why they fell the way they did. There has to be more to the story. Well, when they would show up in architecture school, they'd be laughed out of the building. Because like I said, we had been researching this. We had an explanation for why they could have fallen that way. And yes, the physics do add up. Looks like these stories are making the rounds again. It seems like they show up every couple of years. So I want to take this opportunity to debunk the architectural myths surrounding the Twin Towers. Now, I want to be very clear as to what this video is going to be about, and more importantly, what it's not going to be about. I am only talking about from the moment the planes hit the buildings until they collapsed. What this video is not about is how those planes got there, who knew what when, and all the things that have happened since. While I have my opinions on those subjects, they're outside of my area of expertise. Now, I also don't want to oversell my area of expertise. I was trained as an architect. I am not an architectural engineer. I understand concepts and principles. You don't look to me for math. This video is not going to be about a bunch of calculations. Now, I am going to use drawings to make my point. Drawings are the language of architecture. But outside of the site plans, none of my drawings are going to be to scale. They're diagrams. They're to show principles and ideas. So without further ado, let's get started. To begin to understand what happened, we first have to know what goes into making a skyscraper. And we have to start with Newton. Sorry, folks. I taught architecture classes. You got to put up with me. But don't worry, none of this will be on the test. The reason any building can stand in the first place is because of a subset of physics called statics. Statics are based upon Newton's first and third laws. First law states an object at rest tends to want to stay at rest unless acted upon by a separate force. Simply put, you put a building in a spot, it's going to stay there. You don't have to worry about coming back tomorrow and it being 2 blocks away. This is your best friend. But we also have to deal with Newton's third law. For every action, there's an opposite and equal reaction. In the case of a building, you have 2 elements, the building and the ground. The building is putting weight upon the ground, and the ground is resisting that weight, keeping the building in place. But no building that has ever been built has even pressure across this entire width and breadth. For example, your house, if it has a chimney, that part of the house is going to be heavier than the rest of the house. You've introduced rotation into the equation. This is your worst nightmare because buildings do not do well at dealing with rotation. As long as your ground can resist a greater force than the heaviest force of your building, you're golden. But let's say it just rained, ground is wet. You now have uneven pressure on a soft surface that can no longer resist the downward force of your building. You have uneven settling, and this can lead to disaster. This is why you very rarely ever see buildings sitting on the surface of the ground. That's why we have foundations. But now you're adding different types of soil into the equation. Different types of soils like different types of foundations. Most basic is slab on grade. You're still floating on the surface, but you're spreading the load out over as large an area as possible. You're acting like a raft, just floating out there on the top. But some soils don't like that, especially if it freezes a lot. The soil heaves and moves. That's dangerous for the building. So you go with a footer. You sink the concrete footer down below the frost line, or even better yet, all the way to bedrock. This also allows the opportunity for basements. This is very popular foundation with skyscrapers. But some soils can't support the weight of anything, so you use piles. You sink them down into a layer of soil below that can support the weight, or again, even better yet, all the way down to bedrock. It treats the soil just like water, like a dock, and the building is sitting above everything. The last concept that we need to look at is called a cantilever. This is where you have a structure where one side is supported, but the other side is just hanging out in space. Common example is a balcony. If you have a force pushing down on the end that's unsupported, you've just added rotation to the equation. The side that is supported wants to rotate up and away, just like a teeter-totter. Now, how you get around this is you add weight to the side that is supported. As long as the loads or forces pushing down on the unsupported side stay close to the weight, you don't have a problem. But the cantilever acts like a lever. The more forces get out towards the end of that lever, the heavier weights you have to hold down the end that is supported. A skyscraper is just a giant cantilever. The foundation is supported by the ground. The roof, it's just hanging out there in the air. And the sideways force is the wind, trying to cause the building to rotate, topple over, act like a giant domino. That's why you need massive weight at the bottom of a skyscraper to counteract all those forces. This diagram is trying to show there are a lot of forces at play on a skyscraper. It's one of the reasons why you see the classic form of skyscraper, large, wide base leading up to a narrow top. Traditionally, if you wanted to build up, make a tall structure, you needed to use stone or concrete. But as I've tried to illustrate throughout this video, everything comes at a trade-off. To go up with stone and concrete requires the walls to become thicker, and the openings in those walls, doors and windows, have to be smaller and smaller. But all that changed in the 19th century with the development of the steel frame structure. Suddenly, you could separate the structure from the walls and partitions. The structure was light and flexible, allowed the building to take on almost any shape, and the walls and partitions could become incredibly light and thin, glass even, allowing in large amounts of light and air. But there's a catch. There is always a catch. Steel frame structures, they're lousy at lateral loads, sideway loads. They want to fall over. Just like putting together an IKEA bookshelf and picking it up without the back on it. Way around it is cross bracing, but you've introduced two more problems. First, all the empty open space in that structure that allowed in all that lovely light and air that you wanted, now you're filling that space back up with stuff. You're kind of defeating the purpose of the lightweight frame to begin with. And the second problem, the joint. The structure is only as strong as its weakest point, and always, every single time in every single building ever made, your weakest point is the joint where the beams are connected. The joint has the highest risk of human error. Every single rivet or bolt has to be physically put in by a construction worker who's often hanging precariously high above the ground while they do this very technical and tedious job. Human error is such a known problem, You have to calculate in a certain percentage of extra rivets and bolts in each joint. But your problem is worse than that. Joints are horrible at resisting rotational forces. They want to pivot around themselves, shearing off those rivets and bolts. You never rely on the joint to resist rotational forces. Their only job is to hold the beams together. But fortunately, there's a relatively easy solution to this problem. Lean your light and flexible structure that wants to rotate against something that's really good at resisting rotation, like a giant concrete wall. Oftentimes, you will find elevator shafts and staircases inside these big concrete walls. They have to go all the way up through the structure, so you might as well take advantage of the situation. That big, massive, heavy concrete wall may be great at resisting the rotational forces within that lightweight steel structure, but that concrete wall has added its own rotational force to the building. It's much heavier than everything else, causing that side of the building to want to rotate down and away, dragging the lightweight frame with it. Trade-offs, trade-offs, trade-offs. Now, I've covered a lot of ground, and there's a lot of stuff to keep track of, but you only need to remember two key points. One, a building wants to rotate around itself. And two, you never rely on the joints to resist rotation. You always have to have something else in the system to resist the rotational forces. Let's get back to the topic at hand, the Twin Towers. Now, I want to start with the attack in the early 90s, when the Blind Sheikh and his followers decided to try to blow up the buildings the first time. This one's pretty straightforward and easy to understand. You kick out your foundation, just a matter of time before the building falls over. And in their wildest dreams, if everything worked out, Tower A falls into Tower B, and then they both collapse onto the buildings around them. Complete nightmare scenario. Remember, all the mass and weight of a skyscraper is at its base, in its foundation. That explosion, all it did was put a big hole in the parking garage. People inside the building barely felt a thing, didn't even sway. When people got back together to try again, take a second shot at bringing down the Twin Towers, they realized going through the basement wasn't going to work. They needed to go up higher. But how high was the key? The top, it's too light, so it'd be easy to damage, but there's not enough weight to do anything after the damage happened. Too far down, and again, you're back into the same problem as the basement. Too much structure, too hard to damage it. But there's a vulnerable spot, roughly about 2/3 of the way up. The structure is light enough to do damage, and then there's enough weight and mass above it to actually have something happen after the damage occurred. What they wanted was just snap off the top of the buildings, have them collapse on the rest of the city around it. No one has said evil is stupid. It's reasonable to assume that these buildings would have acted this way. We go back to that diagram I showed earlier. You have multiple forces acting on the building. You have the lightweight metal structure leaning against the heavy concrete structure. Heavy concrete structure forcing itself down to the ground harder than the lightweight structure, causing rotation. You have the explosion. It takes out a good chunk of the building, good chunk of the structure. Suddenly, you have new forces added to the building. You have an extra cantilever that's not accounted for. Suddenly, you have the building with rotation in opposite directions, pulling the building apart. You have heavy loads on that new cantilever, and you have a structure, the metal part, that's not very good at resisting rotational forces. It's understandable that that part of the building would break away, causing extra forces on that concrete structure with the risk of it snapping in the opposite direction. Again, reasonable to assume that this would work. There was one fundamental problem. The World Trade Towers were not built using this technique. The history of the Twin Towers is a convoluted mess. If you go back to the beginnings of New York City, the site that eventually became the World Trade Center, it was underwater. It's only over time as the city expanded that the shoreline moved out, and they filled in the land with whatever crap they could get their hands on. City garbage, old ships, logs, whatever dirt they could find. This was a waterlogged, inconsistent mess. When the powers that be started to conceive of the World Trade Center project in the early 60s, this neighborhood proved to be irresistible. I mean, what was there not to like? Just a few blocks from downtown Manhattan, and the neighborhood was made up of mostly low-rise, dilapidated old buildings. All they had to do was get rid of a few landowners and some tenants. And it's not like a government hasn't done that before. From the beginning, there were problems. A lot of the landlords didn't want to sell, and some of those landlords had some very interesting connections. Let me put it this way. They were used to being the ones who did the persuading. I'll let you all look into that one. But what proved to be the real PR nightmare was that this neighborhood had a major fan club. If y'all are familiar with the work of Jane Jacobs, this is one of the neighborhoods she gushed over in her book, Death and Life of Great American Cities. The city got their way, and they got the property, but at the cost of political capital and goodwill. A lot of hard feelings. But they backed themselves into a corner. They had to put the World Trade Center project on that site or lose a lot of face. Turns out, there was a reason why that neighborhood hadn't been built up. There were no skyscrapers in that part of town. The land wasn't suitable for that type of construction. And so one architect and engineer after another walked off the job. Not me. I'm not getting involved in this. So the city just kept upping the bounty, offering more and more money until they found somebody who'd be willing to take the risk to take on the challenge. But they still had to deal with the site's two major problems: water and inconsistent soil. The ground was so soft and so inconsistent that no traditional foundation was capable of supporting any type of major structure. Skyscrapers are known to act as wicks. You'd be surprised how many floors up they can suck water out of the ground, and that's under the best of circumstances. This site, the water table is just inches below the ground. The ultimate solution is what became known as the bathtub. It's like a giant swimming pool meant to keep water out. It's a hybrid between slab on grade and a footer foundation. You push the slab on grade down in as deep as you need the foundation to go, and then you seal off the sides from the outside with footers. The beauty of this design is that all the buildings could share one foundation. You spread the load out over as large an area as possible. Here's the site plan. The thin black line, that's the outline of the bathtub. The two black squares, those are the twin towers. The gray squares inside the outline, those are the other buildings in the complex. And the black trapezoid to the north, just outside the north end of the black line, that's Tower 7. We'll come back to that in a little later. But the important thing here is all of these buildings' foundations are one. It allows it to float over as large an area as possible while at the same time keeping them all dry. I know I keep repeating myself, but there's just no way around it. Everything comes with a trade-off. For this foundation to work successfully, you need your building to have as even a load across as depth and width as possible. A traditional structure just won't work. You have the light steel frame on one side and the heavy concrete section. You have rotation trying to twist the building. You risk two problems. One, the heavy concrete section could just punch through like a nail through a board down into the soft ground. And the second, it's just the heavy end settles faster than the light end, causing everything, including the foundation, to sink at an uneven rate. And we all know where that ends. The architect and engineers had to design a completely new structure from scratch. The best way to describe it is like a straw. All the heavy structural elements that carried the loads down into the ground, they were on the exterior walls. Everything on the inside was light as possible, floors and columns. This caused all the rotational elements to rotate inwards. While each wall did want to rotate, the opposite wall counteracted it, making the building itself not want to rotate much at all. It was incredibly stable, hardly any sway in a building for that height and slenderness. These floor plan diagrams represent your typical high-rise construction. Light steel frame leaned up against a heavy concrete core. While I talked about the tragic consequences if the building reaches critical mass where it begins to fail and fall, one of the benefits of this system it's actually very hard to reach that level of critical mass. The regularized grid, the structure, a lot of columns going up and down, spreading out the load. You'd have to take out a lot of those columns to reach the point where you have collapse. The second benefit, those thin walls. An explosion treats them like they're invisible. So a lot of the energy that might have gone into the system, into the structure, gets blown out into the air. This causes you to need an even bigger explosion to have results that lead to failure. These floor plan diagrams represent the Twin Towers. Their unique structure was very strong and very rigid. It did an excellent job of spreading the forces out evenly across the ground. The thick exterior walls allowed for the interior to be very light and very open with minimal supports. But wait for it, there's always a trade-off. This structure is the worst possible one for introducing a major explosion up at the higher levels. That thick exterior wall, it's going to contain and redirect the explosion back into the structure, magnify it. And that light, open interior with minimal columns, that explosion is going to do worse damage. You're going to take out a much higher percentage of interior columns. Not a good thing. If there had only been an explosion, the Twin Towers would still be standing today. The structure did its job admirably. What proved to be the building's death blow was fire, all that jet fuel. The explosions took out the majority of the columns, but the remaining columns, it blew off their insulation. Steel is horrible at resisting fire. You don't need very high temperatures before steel starts losing its structural integrity. Even if all the columns on multiple floors had been taken out, the buildings would have survived. The structure could still handle it. But the floors themselves, their structure was also steel, and they had their insulation blown off as well. It was just a matter of time before they lost their structural integrity. And once that happened, one of the floors collapsed down onto the floor below it. This is where the uniqueness of the Twin Tower structure comes into play. In a traditional building, when you take out part of the structure, you introduce new forces into the structure. These forces get spread throughout the building, causing it to rip itself apart, eventually collapsing. There were no forces within the Twin Towers trying to rip itself apart as it began to collapse. Above the collapsing floors, all the pressures, all the forces stayed the same. The only difference was it no longer had an equal and opposite force pushing up. It just began to sink. Below the collapsing floors, also nothing had changed. You still had the same forces canceling each other out, keeping the structure straight and rigid. It's only at the areas where the floors began to collapse that you see changes. The only place that new forces are being introduced into the building is when that first floor starts to collapse. Remember, each exterior wall wants to rotate inwards. As long as they're all connected together by a floor, by the floor structure, those forces cancel each other out. That's why the building itself doesn't want to rotate. You remove that floor, suddenly all the walls want to rotate inward. And as the floors begin to collapse, they're also pulling the walls inwards as well. So that's why you have the building, as the floors begin to pancake, it's literally pulling itself inwards as it falls. It's only as you start to build up debris that can no longer be contained in the building, you start to have the mushroom effect, the building pushing itself outwards. And finally, as it collapses down, it falls into the basement. And that's when you end up with a large pile of rubble. I've given this explanation a number of times over the years. It's not uncommon to hear a similar reply. Yeah, that's all good and stuff. But that building 7, what happened there? That's fishy. Okay, let's talk about building 7. It's called building 7 because there were 7 buildings in the World Trade Center complex. You know how many of those buildings collapsed after 9/11? All of them. So what makes number 7 so special? People will say, yes, but it was outside the bathtub. It shouldn't have fallen. Well, to the south, there were 2 buildings outside the bathtub that collapsed as well. What makes number 7 so special? Remember I said earlier, all the buildings in that complex, their foundations were tied together. There were tunnels that led from the bathtub into number 7. Number 7 had fire damage from the debris falling on it as the buildings collapsed. It also had damage to the foundation as the debris and rubble pushed up through those tunnels up into the foundation of number 7. So again, what makes number 7 so special? I wasn't the one who came up with this analysis, but I was there and watched firsthand as world-class architects and architectural engineers figured out what happened, put things together piece by piece as the information came in, sometimes almost hourly. And I watched them come to the realization, you know what? This building acted the way it had been designed. I find it interesting that people don't stop and think, maybe architects and architectural engineers plan for their building to fail. In the late 60s and early 70s, when the World Trade Center was being designed and built, the world was dealing with the major problem of Islamofascism. The Islamofascists' preferred method of making their point? The bomb. There's a reason why that truck bomb in the early 90s failed. The architects and engineers assumed that at some point somebody was going to try to stuff a bomb in that basement. They even took into account a 707 flying into the side of the building. As I said earlier, if it had just been an explosion, the building would have probably survived. They didn't take into account the amount of jet fuel a 747 carries, which is understandable because 747s hadn't been invented yet. I want to tell you all about my own personal bias, why my BS meter has always gone off whenever I started hearing the argument, well, you know, it really couldn't have happened that way. It comes out of my own personal experience, so take it for what it is. In my department, we had a professor that as soon as 9/11 happened was jubilant. Fist pumps, dancing in the street, telling everybody who'd listen, this is what happens when you oppress people, the voice of the marginalized, the only way that they could address and deal with oppression. Yada, yada, yada. Sound familiar? Well, I was there the day the dean came in and told him, shut your yap, learn to read the room. This isn't the time and place. And he did take the note. He stopped talking, at least in public, but he was still muttering, talking to anybody who would listen, anybody who he thought was a sympathetic ear. But a couple months later, things had changed. Politics had changed. And he was the first one I ever heard start saying, you know, I don't think it could have happened that way. I think there's more to the story. At that time and that place, that crowd, he got laughed out of the building. It was also from that professor that I heard another argument for the first time. Yeah, that sounds good. Makes sense. Assuming the World Trade Center really did have that structure, how come we never heard about that structure before? We're only hearing about it now. Kind of convenient, don't you think? I laughed in that clown's face. I was in architecture school at the time and had taken many classes studying that structure long before 9/11. That structure is famous in the architectural world. It has been in many architectural and engineering publications going all the way back to the 70s. How do I know? I looked it up. I'm not saying you can't sell me a bridge in Arizona, but if you do, you're going to work at it. Part of thinking like an architect means you're willing to reject the premise of the question, your own question if need be. So I got to thinking, why am I relying on my own memory? So I went to the library and looked up the literature, found all the old articles. Well, it gets worse for this clown, because a few years later, politics had changed again. Now he was publicly telling anybody and everybody, if you believe something else happened at 9/11, you must be listening to Rush Limbaugh. I don't know what Rush Limbaugh had to do with it, besides he apparently didn't like him. But then a couple years later, things had changed again, and now he was back to saying, I don't know, this doesn't make sense to me. Seems more to me like this argument is more about causing division and blaming people you don't like as to actually really trying to get to the truth. I expect that at some point you should be asking the question, why should we trust you, Randy? And the short answer is, you shouldn't trust me. Thinking like an architect means you're willing to reject the premise of the question, ask your own questions, and seek your own answers. My purpose here is to provide a jumping off point. There's a narrative out there. I've provided a counter narrative complete with facts as I know them. Facts that can be easily confirmed, double checked. It's up to you whether you want to pursue it, ask your own questions, and find your own answers. When you come from the world of design, you live in the chaos of endless possibilities. You can never clearly define a problem. You have to be willing to make a decision knowing that in the future you may learn that everything you based that decision upon was wrong. And you have to be okay with that, knowing it's okay as long as you made your decision in good faith, based upon the best available information that you could gather at the time. I don't know everything, and I have the humility to recognize that I could be wrong. But until there's new information, I'm very comfortable where I stand. Do you have any new information? I hope I've given you all something to think about, and until next time, I'll be seeing y'all. Oh yeah, and please like and subscribe.
Please like and subscribe. Please leave a comment.